Hey, hello everyone. Welcome to the next video on design of FC TCR. This is a part 3. In this video, we are going to design the control circuit. Previously, we have designed the power circuit and measurement circuit. So let us design the controller circuit for this. So to design the controller circuit, let me take one from block. Okay, so and this from block I will transfer below this. Okay, so how to design the control circuit? Let me take the picture of this control circuit in the screen, so it will be then easy for you to understand the design. Okay, so let me adjust this. So this is my controller design, which is to be designed now. Let us zoom on this part only. Okay, so to design the controller, first I need the QS, and it must be compared with the constant block. So take the block of from QS. I want to reduce the reactive power supplied by the source is to 0. So I'm taking this QS, then take the block of add with the sign of minus plus. Connect the QS block here. Take the one block of constant. Take the one block of constant, and this constant block is connected here. The reactive power I want to reduce it to 0. So I'm making this constant is equal to 0. Now this Q 0 minus QS, it must be passed through a gain of minus 1 because we need a opposite power is to be injected. So this is a minus 1 gain. Then after this gain, we need a PI controller. So in this, sorry, not a pi, it must be PI controller, PID controller. So I will copy this PID controller. Okay, so I will connect this PID controller over here. So in this PID controller, okay, double click on this PID controller. Let me check what are the values I have taken while simulating previously. So I have taken these values as 1 and 0.01. So same values I will take in this circuit also. Double click on this. It will open the dialog box of PID controller. So here you set this P controller value is to 1, integral control is to 0.1. Come to the initialization and integrator initialization, you set it to 135. So initial output of the integrator should be 135. Why I'm taking the 135? Because phase angle variation should be 90 to 180. So between 90 to 180, the center value is 135. I know don't need a D controller. So let's cancel the D controller from this. Once again, I will open this block. Sometimes it takes time to open. Okay, so only PI controller I needed. So in this PI controller, I set this value is equal to 1 and 0.1 with the initial value as the 135. Now here I have to add the limiter. So to add the limiter, that means saturation. So take a block of saturation. In this saturation block, set minimum limit to the 90 and maximum angle limit is to 180. So FC TCR, the TCR only is fired between 90 to 180 degree to get the output power. So here at this we'll get the firing angle in the output. So now this firing angle is to be used to generate the gate pulse. So gate pulse, how this is generated? Gate pulse must be synchronized with your compensator voltage, that is voltage across compensator. So I will copy this block of voltage across compensator. Okay. Uh, this voltage across compensator must be compared with the zero value. So I will take the block of constant, and that means I'm going to design a ZCD, zero crossing detector. So take a block of logical operator. Okay, in this logical operator, connect the block of VC as well as connect the block of zero. So it will compare the values of VC with zero and generate the square pulse at the every zero crossing. So we'll get a zero crossing output over here. After getting the zero crossing output here, now I want to generate the pulse. So how I can generate the pulse? Let me take a view on my previously designed circuit. Okay. So to generate the circuit, so now we need some theoretical base over here. So this angle, whatever the angle you are getting at the output of this angle is in degree. So that degree must be converted into time. So how I can convert the degree into time? So let us check how to convert the degree into time. So angle which is degree. So our India have a frequency of 50 hertz. So one cycle corresponds to 0.02 second. One cycle is corresponds to 0.02 second, and one cycle is equal to 360 degree. So how much seconds per degree? So that can be calculated as in a gain block. Okay, take the block of gain. In this gain block, set the gain is equal to one cycle is for 0.02 divided by it is correspond to 360 degree. So your degree will be converted into seconds. So this is the gain for 1 degree. How much milliseconds are there? So this is connected here. So now whatever the uh, this angle, it is converted into the time domain. As the angle is converted into the time domain, now this much phase shift I need in the whatever the square pulse is generated here. So how I can generate the phase shift? Take a transport delay. Okay, take a variable transport delay. In this variable transport delay, I need to connect the block of this AND block, but output of AND is the Boolean in nature. Output of this is Boolean in nature, so I need a data conversion. So because variable delay block requires the data which is double in type, so I will take a converter in between. So this converter is used to convert. Okay, so here I'm going to convert this my data type. Sorry. Okay, I need this data type. Uh, just a minute. Let me check once again the converter, data converter. Okay, so let me check in my diagram what type of data conversion I have used here. So data type conversion, if I double click to this block, what are the parameters are here? Okay, so the output data type we need a double. So once again I will come into my diagram which was where design. So in converter block you set this data type, output data type to double. Okay, output data type to double. So the Boolean output is converted. Boolean means binary output 0 and 1. It is converted into double. Now this waveform should be shifted by this much delay. Okay, this waveform should be shifted by this much delay. So this is delay is added in the circuit. Now what I need, if I do this delay, then the pulse generation will be of, each pulse is of 0.01 second, that is the 10 millisecond. But I need a pulse for a shorter duration. So how I can generate the pulse for a shorter duration, that we will check. Okay, so how we can generate the pulse for a shorter duration, that output of the first output of this transport delay. Okay, so output of this transport delay, again I will connect one more transport delay here. So this output is connected here. Here I need the delay which is inherent now. So now I don't want a variable transport delay. Okay, so here what I need, just a minute. Okay, just a minute, the system is hang. In the my previously designed circuit where, okay, so here I need a transport delay, not a variable transport delay. I need the block of transport delay. So let me come into the video again. Uh, so instead of this block, I need transport delay. So I will take this transport delay block, and how much delay I required here. Let's check. So I want the pulse only for 5 millis, only for a small millisecond. That is, I need the pulse only for 0.001 second, 0.001 second. I need this pulse. For 8 milliseconds, suppose 0.8 milliseconds, suppose you pulse required. So we can change this is to 0.008. So that pulse will be designed for 0.08, but 0.005 is also okay here. Now, these both outputs are the double, now which must be converted into Boolean. So take the block of, again, you can take this data conversion block. You copy the double data conversion block once again. You connect this data conversion block here. Then set this data conversion type is to Boolean. You choose the Boolean over here. Next, same copy and make it Boolean here. Next here, we want the block of NOT gate. Okay, or you can take a logical gate. In this logical gate, set this output as a NOT gate. This NOT gate is connected here. Now you take an ending of these two. So if the ending operation is taken, that is logical operator is taken, sorry, not a logical operator. Okay. This logical operator and the first one is compared with the second one, so it will generate the pulse of only for 8 millisecond. Okay, so this pulse will be generated only for 5 millisecond, which is set here. and this pulse must be given to O2 block, that is here this pulse is given to this pulse which I am getting here, it must be connected to gate 1. If we collect G1, so it will connect to the G1. Now G1 pulse is ready with me. Now I want to design the G2 pulse. So how I can design the G2 pulse? So to design the G2 pulse, what I need, this delay, G2 pulse must be, the thyristor 232 must be operated after the 180 degree of the first thyristor, after 180 degree of the first thyristor. Hence, what I will do, to design this, I will copy from my previous circuit, so it is easy to explain me also. Okay, so whatever the alpha you are getting, in that alpha you add the 180. So uh, let us come here once again in our circuit where which we are designing. Okay, in this circuit, this you copy the similar block once again. You copy this and paste these all similar blocks. In this block, we want to give this delay such that this delay must be firing angle delay. The firing angle is calculated over here. So we will take a block of add. In this add block, the firing angle must be added with the 180 degree phase shift. So take a block of constant and connect over here. So the phase shift of 180 degree will be created in your phase angle. So 180 degree phase shift. This angle is in degree. To convert it into time, again 0.02 divided by 360 block is to be connected. 0.02360 block is connected, and this block is given to the delay of this. Now whatever the pulse you are getting here, that gate pulse is going to the G2. Okay, so make it global variable. Sorry, in the previous G1 also I have forgot to make it global, so make this G1 also as a global. You can keep the local also because we are not going to use this in another circuit. So if you observe here, this is the total design of my controller. So after running the controller, how the results is to be taken, which results we want to see in the output, that we will see in the next video. So this entire consists of a controller. So let me create this area and let us take this in one area. So this is my controller design where firing angle I'm getting at the output. So this part is a controller up to the saturation block. After that, it is only pulse generating circuit, how the pulse is to be generated. So same logic you can use in the hardware design also to design the circuit. So QC must be equal to 0. So for that, I am taking the VC as a reference and generating the gate pulse. Hope you understand this video. Next video we'll see how to run this circuit and what measurements we have to take at the output. Thank you.